Let's talk about friction. How do you turn your car? How does your car turn? Well, I turn the steering wheel. No. You turn the steering wheel and your wheels turn. But then what causes your car to actually turn? Well, the wheels are turning and it follows the wheels. Well, why does the car follow the wheels? It doesn't want to. And the answer is friction. Everything you do in your car is based on friction. So I hope to completely ruin your life in thinking about what you're doing in your car. Most of it's friction. So start off with a demonstration to introduce some of these points. This is a demonstration of static and kinetic friction. I've got here a string and a cart which can move pretty much without friction along this track when I put it wheels down. When I put it wheels up, it has a fair amount of friction moving along the track and will help me to demonstrate static friction, which is if you hang a mass on the end of this string. This is a 20 gram mass, and the force of gravity acting on this mass is its mass, 20 grams, times the acceleration of gravity, 9.8 meters per second squared. Convert grams to kilograms, multiply by 9.8, and it gives you the force of gravity acting down on this mass. Because the string is stationary and this mass is not accelerating, the tension that pulls up on the mass must equal the weight, its own weight pulling it down. So that tension, we can work it out, just multiply the numbers, and the tension translates over into a tension force on this cart. So the tension in the rope pulls the cart in this direction. There's a gravitational force, the mass of the cart, times the acceleration of gravity pulling it down, and then a normal force up on the cart as well. But what's balancing the tension in the string that's pulling the cart this way? The answer is the static friction force, which operates in the opposite direction. And that's a rule of thumb, and sometimes it can be a little bit tricky to determine the direction of the static friction force. The fail-safe way to figure out what direction it acts is to say, what direction would this move in were there no friction? Well, if this was completely slippery, then the tension would pull it and it would move in this direction. What's the direction of the static friction force? It's in the direction opposite the direction that it would move if there were no friction. So we've now determined tension in this direction, static friction in this direction. Since this cart is not moving, those two forces must balance each other. They must have equal magnitudes and opposite directions. Since the cart is not moving in the vertical direction, the normal force and the gravitational force must also be of equal magnitude and opposite direction. So let's ask about how this static friction force behaves as we add more mass to the end of the string. So there's a greater mass. It's 50 grams. So we've increased the mass, we've increased the force down on this, increased the tension in the string, and therefore increased the force in this direction on the cart. The cart is still stationary. So by Newton's second law, all the forces must add up to zero. The net force must be zero. Therefore, the static friction force must be greater than it was before. If we move then to 100 grams, even greater static friction force to balance the greater tension force. And then at some point, you're going to add enough mass on the end of this string that the cart is going to start to slide. The point at which it starts to slide, we'll talk more about in class, but that's where the static friction reaches its maximum possible value. It can't get any bigger, and then it gives up. And when static friction gives up, the cart accelerates, and another type of friction takes over. Static means stationary, means not moving. So static friction is what you get when objects are not moving, or in some cases not sliding against a surface. They're actually moving but not sliding. But in this case, not moving. Once we've added enough mass to cause this cart to accelerate, then another type of friction is in operation. It's called kinetic friction. It also, in this case, it operates in exactly the opposite direction to the direction of motion. So that kinetic friction, tension is trying to accelerate the cart in this direction. Kinetic friction is trying to slow it down, and its role in life is to dissipate some energy and slow the cart down. It won't go as fast as it would without friction. So let me do the experiment now, starting with this mass pretty up near the top. And you can remember about how fast this is going when it reaches the pulley here. And then we'll do the whole experiment without kinetic friction. Okay, moving along pretty well. Turn the cart over now and ask how fast it's moving when it reaches the pulley. And I think you can see that it's moving considerably faster in the second case. In fact, we've got one of the labs is to study this problem, look at the forces, and but this is a great introduction to static and kinetic friction. Okay. Define the static friction force. Relate its maximum value to the normal force, and define the static friction coefficient. So static friction forces are parallel to the surface of contact. Let me just remind you about normal forces. What direction are they in compared with the surface? Perpendicular. So normal will always be perpendicular to the surface, and static friction will always be parallel to the surface. They're both forces of contact, so-called. And they pertain when objects are not sliding against each other. In the demo video, I talked about the fact that they do pertain when things are not moving against each other, but in some cases, it matters that they're not sliding against each other. For example, well, the car example. You're in your car, you turn your steering wheel, your wheels turn. And as long as you're not on a slippery road or there isn't any ice and you don't turn too fast, then the wheels are always going to roll against the pavement and not slip and slide against the pavement. So what's actually going to turn your car, in that case, when you turn to the left, your wheels turn, is that there's static friction forces between your wheels and the road. And that road exerts a static friction force on your wheels that causes your car to turn. So it's the road that's turning your car, not your steering wheel. By Newton's third law, your wheels exert a friction force on the road in the opposite direction as well. But that's why we say when it's not sliding is when we've got static friction. And they act in a direction that prevents objects from sliding against each other. So we talked about that in the demo video as well. To figure out the direction of the static friction force, you just ask what's the direction it would move were there no friction. And then whatever direction that is, static friction must act in the opposite direction. All right, so we're asked to relate its maximum value to the normal force. So in the video, remember we kept adding weight to the end of that string, and then eventually we got to the point where the static friction couldn't hold on any longer and it gave up and it started moving. It's that maximum point that we're talking about now. The maximum possible static friction force is denoted by this F sub s max. And So the static friction itself in any given situation is always going to be less than that maximum amount. And the maximum amount is related to the normal force. The maximum value is related to the normal force by this equation. Now this equation is approximate. It works quite well in many situations. It doesn't work in all situations, but it gives a good physical feel for what the maximum static friction force does. This maximum static friction force is proportional to the normal force, F sub n. And the constant of proportionality is called the static friction coefficient. And that static friction coefficient depends on what materials you're talking about. If it's a hockey puck and ice surface, that static coefficient of friction is going to be very small. The maximum static friction is not going to be very big with that hockey puck because it slides so well. So that would have a small static friction coefficient. The static friction coefficient for, it basically measures how much friction there's going to be, how much static friction. It's quite large for a tire on pavement because you want it to grip. You don't want it to slide. So this is essentially the same demo that we did. If you're pulling on a rope and you pull with a small amount of force, then the static friction force is going to be fairly small. Pull with a bigger force, the static friction force will be bigger. And then there's some point at which you've exerted enough force on this that static friction gives up, you've reached the maximum and exceeded the maximum, and it starts to move. All right, an example. Block of mass 40 kilograms, and a static friction coefficient of 0.3. Find the largest force F you can exert with a rope without causing the block to move. Well, let's do it. We've got to choose a coordinate system. We've got forces we're interested, so the object is going to be the block itself. We're going to be interested in the forces on the block and the mass of the block and the acceleration of the block. So all of this pertains to the block. So let's ask about the forces on the block. Let's take the x direction to be this way. The force F is in the plus x direction, and the static friction force will be in the minus x direction because it's opposite the direction it would move if there were no friction. So here's a force in the plus x direction. We're asking about the maximum possible static friction force, and just below that maximum it's not going to be moving and not going to be accelerating, so we can put in 0 for the acceleration. So that says that we're talking about that maximum force. This force, the applied force, the force that you're pulling the rope with, is a tension force actually, is equal to the static friction force. Well, we've got forces in the y direction also. So let's take the y direction to be up, perpendicular to x, and let's look at the forces in the y direction. Well, what forces are there? There's the normal force, and then there's the weight of the object. So here's the fully expressed free body diagram. Force to the right, force to the left, force up, force down. Same as in the car example we talked about before. There were 4 forces in the 4 different directions. In the y direction now, the normal force points in the plus y direction. Gravity points in the minus y direction. So we put it in with a minus sign. And it's not accelerating in the y direction. It's not moving at all. If it's not moving, it's not accelerating. And you say, well, wait a minute, don't I just put in g, minus g for the y acceleration? And I say, no. The only time you do that is when it's in free flight. But in this case, you're asking about the motion of the block Is it moving? No. Is it accelerating? Well, accelerating means that the velocity is changing. So it's not accelerating. So that acceleration has to be 0. So the normal force equals mg. We can work that out. The normal force is the mass times the acceleration of gravity, and that's the apparent weight, right? And that's equal to 390 newtons. And then finally, from the last concept, we can calculate Fs max to be the static coefficient of friction, static friction coefficient, mu. This is a Greek letter mu. I think we talked about that once before. We were talking about the micron. Mu, mu s, is the way we refer to it, mu s, times the normal force. Well, we know mu s, we're given its value, it's 0.3. Normally these static coefficients are between 0 and 1, though they can be occasionally found to be slightly larger than 1. Times 390 newtons, I guess I just didn't round it when I was here, but anyway, these numbers are supposed to be the same, equals 120 newtons. So that is the maximum possible static friction force that you can get for this particular situation, where you've looked up the static coefficient of friction between a wooden block and a table, for example. What force holds the book up? Well, what are the forces on the book? Gravity. What other forces? The hand's pushing on the book. What kind of a force is that? This hand on this side, on the right side, pushing on the book, that is a normal force because it's perpendicular to the surface of the book. There's also a normal force of the other hand on this left side, pushing the book the other way, and those two forces are going to cancel each other out. But what's holding it up? These two guys don't hold it up. Gravity certainly doesn't. And you say, well, the only thing left is the friction force, and you're right. There's a friction force, static friction force, of this hand on the right side on the book, holding it up. And there's also a static friction force on the other side holding it up. And it's these two static friction forces that are responsible to hold the book up. That's similar to what happens in the amusement park ride, where, I forget what you call it, but you stand against a wall, and then this disc spins, and then the floor drops out. What holds you up? And the answer is static friction. And you know it because if you've ever been on a ride like that, it kind of pulls your clothes up this way. It's holding you up by your clothes, and it's a static friction force that holds you up. What holds her up? Same thing. Static friction. She's got a vertical wall here, a vertical wall here. She's what's known as mashing or climbing shoes against the walls. And static friction is holding her up. So thanks to static friction for you climbers out there. You definitely need static friction. Define the kinetic friction force. Relate it to the normal force and define the kinetic friction coefficient. We talked about this in the demo as well. Kinetic friction forces are parallel to the surface of contact. Again, parallel, like static friction. But in this case, they pertain when objects are sliding against each other. And they act in a direction that opposes the sliding motion. At the end of that demo video, we had the case where I demonstrated how fast the cart would accelerate with a lot of friction when I had it tipped over with its wheels in the air versus how much it accelerated with the wheels down. But that kinetic friction force was always opposite to the direction of motion, slowing down the motion and leading to less energy. So the equation is very similar to the one for static friction. The K here denotes kinetic instead of static. Mu K is the kinetic friction coefficient. It has a K, a subscript K, to remind us that it's kinetic, meaning moving. And then it's proportional to this normal force. The difference between this one and the static friction case was that this equation for the static case was that the static friction is mu static times it only pertained for the maximum case of static friction. And but here this pertains for all values of kinetic friction. You take the normal force, you multiply by the kinetic friction coefficient, and you get the kinetic friction force. All right, here's some values of the static friction coefficient and kinetic friction coefficient. So I would like to point out this one. Rubber on wet concrete. So it's 4 down. The static friction coefficient is 0.7. And that relates to the maximum possible static friction force. And then 4 down on this column is 0.5. So the coefficient of kinetic friction is smaller than the coefficient of static friction. What does that tell you about anti-lock brakes? And the answer is that what anti-lock brakes want to do, in the old days, when we didn't have anti-lock brakes, you step on the brakes, you lock your wheels, and then you slide along the road. Well, sliding along the road means kinetic friction, and it means a smaller kinetic friction coefficient. It means you're going to get less stopping power when you're sliding than when you are gripping the surface. So if you step on the brakes, so forget about anti-lock brakes now, but step on your brakes just a little bit, and you're not stepping on them enough to cause your brakes to lock and them to slide along the road, but instead you're getting some grip on the road, you can potentially get a lot more stopping power by using static friction than kinetic friction. And so what anti-lock brakes do is they try and just hover around that fine line between right on the edge of that static friction force giving up. So they want to get as close as possible to this maximum possible static friction force, which will give them this higher, which will make this coefficient come into play. And so what they do is they kind of pump it on either side of this point. It's called the point of slipping. They put on a little bit more brakes, and then the car wheels start to slip a little bit, and then the circuitry detects the slippage, and then it backs off on the brakes a little bit to bring you back into a gripping and rolling motion instead of a sliding motion. So that's what anti-lock brakes are all about. And so if you have anti-lock brakes on your car, in the old days we used to pump our brakes to try and find that right at the point of slipping but not beyond it. But anti-lock brakes do that for you. So if you have anti-lock brakes and you're on a wet road, or even worse, an icy road, just push down on the brakes and let the circuitry do all the work. And that's the design anyway. Teflon on Teflon, these coefficients are very, very small because Teflon slides really well against itself. Glass on glass, ice on ice, et cetera, et cetera. So that's the idea there. Another demonstration. Block of wood, a plane that I can raise and lower. I'm going to demonstrate the forces on a block that's stationary on a plane. If the plane is horizontal, there will be a gravitational force down on the block, pulling it down toward the center of the Earth, and a normal force perpendicular to this horizontal surface, pointing vertically upward. Those two, because the block is not moving, those two forces must have equal magnitudes in opposite directions. If we raise the plane up a little bit and put it at a certain angle, we introduce a third force. We've still got gravity pulling it straight down toward the center of the Earth. We still have the normal force, and in this case, well, as before, the normal force is perpendicular to the plane here. So it's not quite vertical now. It's off at an angle that's exactly 90 degrees from this direction. And we have one more force, which is stopping this block from sliding down the plane. It's the static friction force that stops it from sliding. If there were no friction, the block would slide down the plane. And that tells me that the friction force must be in the direction opposite the direction it would move if there were no friction. If we increase the slope, we get to the point where static friction is no longer capable of holding the block up the plane, and the block accelerates down the plane. And we can study that problem as well using kinetic friction instead of static friction. That's blocks and planes. All right, let's do an example. Kinetic friction brings a sled to a stop. So here's the child on the sled moving along at 4 meters per second. And a little while later, the child stops. And it's kinetic friction that's slowing him down. Why? Because the sled is sliding along the snow. Find the stopping distance. So this one actually combines our knowledge of Newton's second law and the forces with our understanding of chapters 2 and 3 of kinematics. Let's see if we can do it. Let's choose a coordinate system, x to the right. Let's draw a free body diagram. So I've got my forces drawn here, normal force up, gravity down, kinetic friction to the left, because it opposes the motion to the right. It tries to slow the sledder down. If you get it wrong, then you're going to have the sledder accelerating along a flat surface, which is kind of embarrassing. So those are forces. The direction of the acceleration, well, what can we say about the acceleration? He's moving to the right. The velocity is in this direction. What's the direction of the acceleration vector? The velocity is going to the right, but it's slowing down. So is the acceleration to the right or to the left? Is it down? Is it minus g? Well, it's certainly not down, because we've got the Earth that's stopping him from falling down. The acceleration is only minus g when it's a projectile motion. This is not that. We got a normal force holding him up. The velocity is only in the horizontal direction. The acceleration cannot possibly be in the vertical direction or in the downward direction, because there's no velocity in the vertical or the downward direction. And the acceleration is the rate of change of velocity. So, having established that the acceleration must be horizontal, either to the right or to the left, which direction would it be in? And you say, well, let's see, if it were to the right, he'd be accelerating, he'd be going faster and faster, so it must be to the left. And that's exactly the way that you come about this conclusion. The acceleration is to the left. Now, I've actually chosen, I've departed from my convention of putting the x direction in the direction of acceleration. It's a free country, you can do it either way you want. If you take the components correctly, it'll work out correctly either way. Let's go ahead and take the x direction to the right, knowing that the acceleration is to the left, and expecting that the x component of this acceleration will be negative, because the acceleration is pointing in the direction opposite x. So we're expecting to see an x component of acceleration that's negative. All right, let's plug in the equations. The sum on forces in the x direction, and these are the, we've got a coordinate system. We've talked about acceleration. We've got a coordinate system, x and y like this. Now we're doing equations, and then we just have to solve them. Here's our equations. Forces, let's look at the forces in the x direction for this sledder. Here's the x direction. This normal force is pointing only in the y direction, so it does not have a component in the x direction. Same for gravity. Pointing down doesn't have a component in the x direction. The only one that does is this kinetic friction. Is it pointing in the plus x or the minus x direction? You say, well, minus x. So we put it in with a minus sign, and that's equal to the mass times acceleration in the x direction. And solving this for the acceleration, we find the acceleration is minus fk over m. All right, let's look at the y equations. Start off with Newton's second law, the y component of the Newton's second law, and ask what the forces are in the y direction. Well, there's a normal force in the plus y and a weight in the minus y. There's a normal force in with a plus sign, plus y direction. The weight is mg with a minus sign, meaning the y minus y direction. The acceleration in the y direction is 0. You go, wait a second, it should be 9.8, right? Ay is always 9.8. No, remember we went through the argument that we've got a surface here, and there's no motion in the y direction. There cannot possibly be an acceleration in the y direction if there's no motion in the y direction. So that the component of acceleration in the y direction is just plain 0. Remember, when you're thinking about the accelerations, you've got to think about the motion, what direction it's moving in, and how the velocity is changing in order to appreciate what the accelerations are going to be and what those different components will be. Well, if it's 0 on the right-hand side, then the normal force, the magnitude of the normal force, we take the mg over to the right-hand side with the plus sign. That'll be mg. All right, we've got a couple of equations here. We're getting lots of equations, lots of symbols, but have no fear. On a lot of these kinds of problems, you're going to do the forces in the x, you're going to do the forces in the y, and then you're going to do some kind of relationship between the kinetic or static friction and the normal force. In this case, we're dealing with kinetic friction. So the magnitude of the kinetic force, F sub k, kinetic friction force, equals the kinetic coefficient of friction times the magnitude of the normal force. Well, luckily, we have a lot of what we need here. The normal force we already know is mg. So we can substitute mg in here, and that gives us mu k times mg. And we can see how we did the algebra here. Oh, all right. So fk is mu k times mg. So I'm going to substitute this into here. So if I do so, I've got the acceleration in the x direction equals minus mu k mg, goes in here, divided by m. So that's the minus sign. That's this minus sign here. Mu k mg, that's the fk. And then we're dividing by m. But lo and behold, and this occurs in a lot of these friction problems, mass cancels. Pretty cool. Mass cancels out. And we simply get minus mu k times g. Mu k, we're told, is 0.05. G is 9.8. And you say, well, g didn't come in as minus, ay wasn't minus g. That's not how it came in. And I say, you're right. That's not how it came in. It came in because the normal force was related to the weight mg. It came in the weight term. And this gives us the component of acceleration in the x direction. Should we be surprised that this is negative? And you say, no, we already worked that out. We expected it to be negative because it's moving to the right and it's slowing down. So we've gotten the acceleration, but we still haven't found the answer to this problem. The coefficient of kinetic friction is 0.05. Find the stopping distance. But now this problem, now that we know the acceleration and we know the initial velocity, this becomes a problem that we could do in Chapter 2 or Chapter 3. But before I finish the problem, I would like to just point out that, that memorizing, for example, memorizing this equation is not going to help. Memorizing this equation is not going to help. If you want to, and I want all of you to succeed, you've got to start with the Newton's second law, figure out what the forces are, and take it step by step. That's the only way to get these kinds of problems and understand them correctly. All right. So let's find the stopping distance. Well, now we know the acceleration, and we can go back to chapter 2 to find the stopping distance. And what we'll do is we'll start off with this equation, the velocity equation, and we'll say Vx, that's the final velocity in the x direction. Well, what's that? Well, it's 0. V naught x, that's the initial velocity in the x direction, that's 4 meters per second. Ax we know, minus 0.49 meters per second squared times t. So we can solve for t, we find t. It takes 8.16 seconds for that kid to stop on his sled. But we're looking for the stopping distance. So it's a long old problem. Lots of steps, but you do the dynamics first, the Newton's laws, faces, use the faces stuff. A lot of times you'll have to find the acceleration. Then once you find the acceleration, you go back to do the kinematics and determine what the stopping distance is. Now we know the time. Now we know everything we need to find the stopping distance. If the initial position is 0, the initial velocity is 4 meters per second, the time is 8.16 seconds, plus 1/2 times the acceleration, which is a negative 0.49 meters per second squared. And you say, well, shouldn't I put it in as a positive? I say, no, sirree. Leave it as negative because x is going to the positive direction and ax is negative and it's trying to slow it down. Otherwise, it'll never stop if you put this in as positive. Times t squared. Plug it in, you get about 16 meters for the stopping distance. That's how to do that kind of problem.